All right, so now we're going to talk about something known as resonance structures. So resonance structures represent different possible structures that a molecule can have, but that have the same overall geometry. And these atoms are sharing electrons within the molecule itself, and you'll see what I mean in just a few minutes. Okay, so what I'd like you to do is to get out a sheet of paper and draw the molecule that's C6H6, 6 carbons and 6 hydrogens. Rather than making the carbon a chain of carbons in a row, I want you to wrap that chain around and make a ring out of it so that the carbons go in a ring around 6 of them, and then attach the hydrogens to each carbon. Let's see what you make. Pause the video, see what you draw. We'll check it out in a second. Okay, so assuming that you have drawn the molecule, did you draw something that looks like this? Realizing that each carbon would have to be bonded to other carbons, and each carbon would be bonded to one hydrogen, that makes for 3 bonds, but carbon needs 4, so we're going to have to put a double bond somewhere. So what you should end up with is a pattern of alternating double bonds and single bonds going around the ring to make sure each carbon has 4 bonds. Okay, so is that what you drew? Or did you draw something like this? Now notice when you look at this one, the double bond at the top is not at the left, but it's on the right. And that reverses where every double bond is, because instead of being in this middle section, that moves this one down to here, and instead of being down in this corner, that moves it to there. So, which one did you do? Did you do the left one, or did you do the right one? Does it matter? Are they the same? Both of these representations are true. Both of these representations allow for the carbons to follow the octet rule. So good job if you made either one of those. But which one is it? Was it the left one or was it the right one? Was it this one or was it this one? Now some of you might be thinking, does it matter? I mean, aren't they the same? Well, on this one, the double bond is on the left side, and on this one, the double bond's on the right side. But you might be thinking, but what if we just took this molecule and rotated it 180 degrees in space, if we just flipped it over? If you were just to kind of flip it over, then that double bond would end up in that location. That single bond would swap over to this location, and so forth. And you're right, if we were to simply rotate the molecule, you would end up getting each of those 2 possible shapes. So is that it? They're the same, it's just which direction are we looking at it? Well, not exactly. Something else is going on. Both of these representations are true, but they're not accurate to what's really going on in this molecule. Because both of them are true simultaneously. And I don't mean simultaneously as in you're just kind of flipping it around and flipping it around. I mean they are both true at the same moment, even when not flipping it. This carbon does experience double bond on this side and a double bond on that side. It experiences a single bond on this side and a single bond on that side, and not by flipping it. And I'll show you how we figured out that that is the case. So if you were to combine these 2 representations, what you'll notice is that every carbon is bonded to 2 other carbons, and there are a total of 3 bonds that are being shared between those 2 carbons. So if you were to average a double bond and a single bond, or cross the 2 different directions, you end up with an average bond strength of 1.5 bonds. So we call these resonance bonds or partial bonds, these bonds that are being shared between atoms. Now in that rotational piece that we were talking about, we are moving the atoms around and looking at them in a different way. But this is not what's happening in this case. The atoms are not moving, it's the bonds that are moving. It's the electrons that make the bonds that are moving. So we represent these partial bonds, these resonance bonds, with a dashed line. They are not a full strength bond, they are a partial bond. Now we know each carbon has at a minimum one bond, so we can draw that with a solid line. And then we can draw this resonance bond with a dashed line. And you'll notice we can draw a dashed line there and a dashed line there because we were talking about the top. In addition, we've got a single and a double here and here that's turning into a double and a single, so we can draw dashed lines there. And we've got a double and a single and a double, so we can draw dashed lines there. And each of those dashes represents a half of bond in strength because that bond's being shared between two different atoms. So how do we know this? Well, one of the ways that scientists figured out that this wasn't just a situation of us rotating the molecule and looking at it at a different angle, but rather the electrons themselves moving was by marking the atoms so we know which ones we're looking at. So the way you can mark the atoms is by using a different isotope of it. Remember, isotopes don't change the chemical properties of the atom, they just change the mass. And so, for instance, we could take something like carbon 13 or carbon 14 and place them in these two locations on the molecule. The others are your normal carbon 12. Now, if you were to rotate the molecule, let's say we rotated it 90 degrees. By rotating it 90 degrees, you'll notice that the double bond that was here has rotated down to be in this location. The single bond that was here has rotated down to be in this location. So that's what it would look like if you rotated it 90 degrees. If we were to flip it around 180 degrees to make for a mirror image, it should look something like this, where that single bond between the two marked carbons simply flips to the other side. So if we flip it over, those two marked carbons ought to still be attached by single bonds. So no matter how we look at it, whether we rotate it 90 degrees down, whether we flip it around, no matter what angle you look at it, under this scenario, the two marked carbons should still always be bonded with single bonds. But that is not what we observe. What we observe when we actually look at these marked carbons is that the double and the single bonds are being shared between them. You could think of it as it could look like this or this. As it turns out, it doesn't actually look like either at any one moment in time. It looks like both of them combined as the average bond strength of 1.5 instead of 2 and 1. It's not the atoms that are moving or our perspective that's moving, it's the electrons that are moving. They're delocalized and able to move around the ring. So if you want to know, well, how strong is the average shared bond? Here's a couple of things you're going to do. You're going to add up the total number of bonds being shared, and you're going to add up the number of atoms that are sharing them. So in this particular ring, you've got a situation where you've got 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds being shared total, and they're being shared among 1, 2, 3, 4, 5, 6 carbons. 9 divided by 3 is 1.5. 9 divided by 6 is 1.5. So the proper way to represent this molecule would be to draw it like this. We know that each carbon is singly bonded to another carbon, and there's a half bond that they're splitting, that they're sharing. That is what we call a resonance structure. Okay, we'll do a little more practice with resonance structures in the second video.